Welcome back to the Deep Dive. Today we are strapping in for what might be one of the heaviest, literally engineering challenges we have ever tackled. Electrifying the industrial workhorse of construction, the cement mixer truck.
It sounds, deceptively simple on the surface, but I assure you, controlling a 400-volt high-voltage system that is constantly managing the motion and energy of a massive rotating drum.
Full of aggregate, water, cement.
Exactly. It's arguably far more complex and definitely more safety critical than just optimizing the drivetrain of a standard passenger EV.
I agree completely. The stakes are profoundly different. If you mess up the power control on a passenger car, you pull over and call roadside assistance.
Right, an inconvenience.
But if you mess up the control on a mixer truck, you face two immediate catastrophe scenarios. Commercially, you could scrap an entire batch of concrete, a concept the industry calls muffling, where the concrete actually sits inside the drum.
Which is a nightmare scenario, a very expensive nightmare.
Or, even worse, you trigger a major high-voltage safety incident on the road or the worksite. This isn't just vehicle control, it's mobile process management.
That's why our focus today is on the central intelligence governing all this complexity, the Supervisory Controller Unit, or SCU.
Okay.
We are analyzing an in-depth consultancy report, specifically designed to build the engineering capability for this system, alongside DVP&R matrices and essential functional safety documents like the HARA and the FSC.
So what's our goal here?
Our goal is to really understand the complete functional specifications process for this P2 hybrid system, which has to seamlessly integrate 24-volt chassis systems with a 400-volt electric power takeoff, or ePTO, platform.
And the SCU here isn't just an equipment controller. It's been elevated in the spec documents. I saw it defined as the energy and motion orchestrator for the entire upper body system.
It is. We're essentially looking at a brain designed for a harsh, mission-critical, mobile industrial system. It's not just a standard vehicle controller.
And we need to see how the engineers managed to meet 5 key performance pillars: raw power delivery, fuel economy gains, ISO 26262 safety rigor, operator comfort, especially noise reduction.
And extreme environmental adaptability.
Okay, let's unpack this. Starting with the external regulatory pressures that mandated this entire complex architecture in the first place.
Right. The transition to this, highly complex hybrid solution wasn't driven by convenience. It's a direct response to escalating global regulatory demands.
And it seems like this hybrid architecture specifically targets 2 major pain points for the construction industry: localized noise and engine emissions.
Those are the big two.
Noise is a massive hurdle for urban construction logistics. We're seeing mandates like EU 540-2014, which says exceptionally strict noise limits for low-speed operation, especially in residential areas.
Exactly. And the electric upper body gives us the perfect tool to manage that. The SCU must fully support a dedicated silent mode.
Which is for what, exactly? Nighttime urban operations.
Precisely. Unloading at a major residential site after hours. By running the drum purely off the quiet 400-volt electric motor, the SCU ensures noise levels stay below a critical threshold of 72 dBA.
Hold on, 72 decibels. For our listeners, that's roughly the loudness of a washing machine or maybe a vacuum cleaner.
That's a good comparison.
So how does the SCU guarantee that noise level compliance? Is it just a matter of turning off the engine?
It's a bit more subtle than that. Yes, the core of the strategy is the engine being completely shut down. But the SCU also manages the power flow to ensure the electric motor is delivering the minimum optimized torque needed for agitation.
Why minimum?
To avoid high currents that might generate secondary noise like fan noise from the inverter cooling system. It's all about finesse. That 72 dBA is often the legal threshold that separates a viable night job from receiving hefty municipal fines, or worse, losing permits entirely.
And on the emissions side, we see the pressure from EU and RMM State V, the non-road mobile machinery regulations, that specifically targets the auxiliary power units that traditionally run the mixing system.
Right, and that regulation pushes hard for pure electric operation of the mixer body. This necessitates a very specific, carefully managed strategy called the Engine Stop Upfitter Continue strategy.
And the SCU is the coordinator there.
It's the brain. It monitors the operational state and the battery SOC, and when conditions permit, like during long idle periods or stationary mixing, the SCU commands the VCU to shut down the internal combustion engine entirely.
But it seamlessly maintains power from the 400V battery pack to the electric motor.
Exactly, for continuous low-speed agitation. This maximizes compliance and fuel savings, all while crucially maintaining the consistency of the concrete.
So environmental and economic factors force the hybrid design, But now we enter the realm of non-negotiable safety requirements due to the high voltage. We are dealing with a 400-volt system right next to the operator.
And that's where global standards like UNES R100 and China's GB 1E384 come in. This moves us into the realm of ASIL-D, the highest safety integrity level for specific failure modes.
So the SCU has what, like a few key monitoring jobs?
It has 3 absolutely critical, non-stop high-voltage monitoring roles. The first is insulation monitoring. High-voltage systems must maintain robust electrical isolation from the chassis ground.
What are the parameters here? What happens if that insulation is compromised, say, by a stone or concrete slurry damaging a cable sheath?
The requirement is incredibly stringent. The SCU must continuously monitor insulation resistance, maintaining it above a critical threshold of 100 ohms per volt DC.
For a 400V system, that means?
Above 40 kiloohms. If that resistance drops below the threshold indicating a path to ground, even a partial one, the SCU executes an immediate mandatory power down strategy. It cuts contactors to isolate the battery pack before a dangerous fault can occur.
And the power down sequence itself is tightly regulated. It requires active discharge control, specifically mentioned in GB 12384. Why is a simple disconnect not enough?
Because when you open the contactors to the battery, you still have large capacitors in the motor inverter, the DC bus, that hold a dangerous charge.
Right, they can hold hundreds of volts for a surprisingly long time.
They can. Active discharge control means the SCU must orchestrate a controlled rapid energy dissipation. The mandate is crystal clear. The SCU must guarantee the high-voltage bus is discharged, or made safe, to below 60 VDC in an incredibly short time.
How short?
Less than 1 second.
Wow.
This requires microsecond coordination with the MCU to use the motor windings as a resistive load for rapid discharge, safely eliminating that stored energy.
That's intense. Now, the third safety mandate is collision detection, referencing FMVSS 305. I find this fascinating because it shows how the SCU, which manages concrete, is also integrated into core vehicle safety systems, demanding ASIL CD levels.
That connection is vital. If the chassis crash sensors detect an excessive acceleration spike indicating a severe impact, or, critically for a vehicle of this type, a high rollover risk,
It can't wait for a CAN message.
it cannot. The SCU must be prepared to cut the main high-voltage relay via a hardwire protection circuit. High-voltage power must be terminated instantly upon crash detection to prevent cable damage from leading to fire or electrocution risk for first responders. That level of physical redundancy is what moves it into the ASIL CD realm.
So, we've covered the regulatory crucible, but here's where the engineering requirements become truly unique. The challenging operational design domain, the ODD. This dictates not just the software logic, but the unforgiving choice of physical hardware.
We're not talking about a passenger car here, not even close. Heavy-duty construction environments are brutal. We need SCU hardware specified to function from minus 40 degrees Celsius all the way up to plus 85 degrees Celsius.
That thermal range alone requires specialized, often automotive-grade or even military-grade components, doesn't it? Standard commercial electronics would just fail immediately.
Precisely. You need industrial-grade passive components, specific semiconductor packaging, and rigorous temperature cycling tests in the DVPNR. But the thermal challenge has an extraordinary caveat that defines the SCU's mission priority,
Which is?
preventing that concrete muffling we talked about.
Tell us more about this unique requirement. It sounds like the SCU is willing to sacrifice itself for the concrete.
It fundamentally changes the design philosophy. In a standard vehicle, if an electronic control unit, an ECU, gets too hot, its internal thermal management system mandates desherating or even shutting down the unit to protect the expensive hardware.
Right, self-preservation.
Here, the SCU's functional safety requirement regarding concrete quality. It actually supersedes its internal protection requirements. In conditions of extreme heat, the SCU should prioritize keeping the drum moving over protecting the controller from minor thermal derating.
That's incredible.
If the concrete sets in the drum, the economic damage and time lost are catastrophically greater than the cost of potentially replacing an overheated controller. The SCU must issue thermal warnings, but the drum movement remains paramount until failure is absolutely certain.
That's a fascinating inversion of standard automotive safety logic value preservation over component preservation.
It reflects the SCU's true identity as a mobile industrial system controller. And on top of that, the external physical protection required is immense. It's exposed to concrete, slurry, aggressive dust, high-pressure washing.
We're talking IP ratings here, right?
We need IP67, which covers dust ingress and temporary submersion. but the specs often escalate to IP69K.
And IP69K is?
It's crucial because it means the enclosure must withstand high-temperature, high-pressure water jets, which are the standard method used in construction yards to blast dried concrete and debris off the truck body. That's a requirement far beyond what a typical passenger car component ever faces.
Finally, let's talk power transients. The sources mention EMC resilience via ISO 7637. This is the controller fighting its own high-energy, electrically noisy environment.
You are dealing with a truck chassis that has massive inductive load starter motors, hydraulic pumps, large solenoids switching on and off a 24-volt system right next to a 400-volt inverter generating high-frequency switching noise.
And then there's the load dump scenario.
The load dump scenario, where the alternator's field is suddenly disconnected while supplying current to the battery, generates violent voltage spikes.
How violent are we talking?
The SCU hardware must withstand extreme load dump pulses, specifically cited up to plus 174 volts, or even severe bidirectional transients swinging from minus 150 volts to plus 100 volts.
Wow.
Surviving that kind of electrical violence while maintaining continuous ASIL-CD functional safety integrity is a monumental hardware design challenge. It requires complex filtering, transient suppression diodes, and a highly resilient power supply design within the SCU itself.
Okay, so now we move from the external requirements and hardware challenges to the internal blueprint. How does the SCU position itself within the complex electronic and electrical topology, acting as that energy and motion orchestrator?
Well, the SCU sits at the nerve center of the upper body domain, mediating requests and statuses across the entire platform. It is explicitly defined as the application master for the mixer system.
It doesn't drive the chassis, but it dictates the energy use.
Exactly. Therefore, it has critical interfaces. Communicating with the VCU, the chassis vehicle controller, asking for engine start, the BMS, the battery management system, asking for power limits, and SOC.
The MCU, the motor inverter controller for the drum.
Right, sending the final torque command. And the remote RX for interpreting operator inputs.
So it's synthesizing data from all these disparate sources, chassis speed, battery health, operator request, to generate the final precise torque command for the motor. That sounds like a nightmare traffic cop directing high-speed data.
It is, which brings us to the necessity of the system's communication strategy. Because safety and reliability are paramount, especially given the high electrical noise from the 400V inverter, the system employs a 3-bus segregation strategy for the CAN networks.
Okay, so this isn't just a software layer. This is physically isolating critical paths.
That has to be physical.
Why can't we just run everything over a single high-speed CAN bus? Is the physical segregation due to redundancy requirements, or is it purely electrical noise? And what's the cost trade-off?
It's a combination of both, but primarily noise and safety partitioning. Running everything on one bus means a fault on a non-critical component, say a faulty temperature sensor, could flood the entire network.
And that could delay or corrupt a life-critical safety message.
Potentially. The cost of running 3 separate shielded CAN infrastructures is high, but the price of failure in ASIL-CD systems is much, much higher.
Walk us through the segregation strategy.
Okay, so we have CAN 1, the vehicle bus. This handles general chassis data, diagnostics, and HMI information, the less safety-critical, slower communication that can tolerate some delay.
Then you have the body stuff.
Right. CAN N3, the Bodio bus. That's dedicated to body-side components like the remote controls, chute actuators, and low-speed sensors.
And CAN 2, the drive bus, sits in the middle as the dedicated backbone.
CAN 2 is the core. It's the high-priority, isolated link. This bus carries only the critical, real-time controlled data torque commands, SOC limits, and safety monitor messages between the SCU, the MCU, and the BMS.
And because it runs physically near the 400 volts, high-voltage cables.
It requires specific physical resilience, heavy shielding, and precise termination to resist that high-frequency 400V inverter noise and maintain signal integrity. The timing requirements are extremely tight here, often demanding latency under 10 milliseconds for torque commands.
That physical resilience extends to the hardware connections themselves, giving us a real sense of the physical burden on this off-highway controller. Just how many inputs and outputs are we talking about to manage the mixer body?
We're talking about massive I/O complexity. The specifications demand a minimum of 16 digital inputs. This includes the standard mode selection switches, but critically redundant lines for the e-stop button and the high voltage interlock loop, or HVIL.
Okay.
We need at least 12 high-side digital outputs for driving large relays, contactors, and high current lights. We need 6 dedicated PWM outputs for proportional valves, and finally, 12 analog inputs for continuous monitoring of pressure, temperature, and drum position.
Let's focus on one of those critical inputs, the high-voltage interlock loop, the HVIL. That's the digital panic button chain that prevents electrocution.
It's a non-negotiable safety feature required by every high-voltage standard. The HVIL is a low-voltage signal, often 12V or 24V, that is literally daisy-chained through every single high-voltage connector. HV connectors, service plugs, battery connections, all of them.
So if any high-voltage connector is even slightly disconnected or damaged,
The low-voltage loop breaks instantly.
and the response time requirement is what makes this so challenging.
Absolutely critical. If that low-voltage loop breaks, the SCU must not only detect it, but must trigger the emergency HV off command, cutting the drive power and isolating the battery in less than 10 milliseconds.
10 milliseconds.
That requirement necessitates that the SCU's input hardware handles the signal directly, bypassing the standard operating system layers, often using dedicated interrupt lines or a watchdog mechanism to guarantee that lightning-fast response.
Now we get to the core of ISO 26262 compliance, the SCU software architecture. You can't put ASIL-D functions next to standard functional code. This is where the rigorous software partitioning comes in.
This partitioning is the backbone of achieving ASIL compliance. The software is conceptually and often physically split into two domains that run, frequently utilizing redundant processing cores or time-partitioned operating systems.
Okay, so on one side we have the functional partition.
That partition contains the logic that makes the mixer work efficiently and accurately. These are the ASIL-A or ASIL-B level functions, the mode manager, the complex PID drum speed controller, the energy management logic, and the HMI handlers. These functions are complex and focus on performance.
And on the other side, we have the minimalist, independent, high-integrity watchdog.
The safety partition. This runs only the highly critical monitoring and arbitration logic, typically assigned ASIL-C or ASIL-D. We see distinct modules here: the torque safety monitor, the direction safety arbiter,
which prevents high-speed reverse regardless of operator input.
The HV safety monitor, and the CAN safety monitor. These modules monitor the outputs of the functional side and the inputs from the sensors, independently validating every single decision.
This leads to the central dogma that defines their relationship, the safety gate principle. Can you give us that accessible analogy the listeners love?
Sure. Think of the functional partition as the eager, performance-focused teenager driving, asking for maximum speed or torque based on the immediate command. The safety partition is the wise parent in the passenger seat with their own independently controlled brake pedal and speed limiter. The vehicle's motor control unit only ever listens to the minimum of those two inputs.
So if the functional partition asks for 500 Newton meters,
But the safety monitor, having detected an issue like an open HVIL or a speed sensor failure, calculates that the safety limit must be 0.
the final executed output is 0.
The final executed output is 0. That simple overriding minimum function is the core of ASIL compliant safety, always arbitrates the final motion command.
Okay, moving away from the hardware integrity, let's talk about the control itself, starting with the master state machine, or FSM. This FSM is the logical workflow that dictates the upper body's mission profile.
The FSM tracks the concrete's life cycle, moving from I-night through standby into operational modes like loading, agitating, discharging, cleaning, and maintenance. However, the foundational design principle is safety dominance.
What does that rigorous term, safety dominance, imply for the FSM flow?
It means the fault and e-stop states are transcendent. They must be able to interrupt any active operational state immediately, regardless of what the operator is doing or what cycle the machine is in.
And a severe fault state can't just reset itself.
It cannot. It cannot automatically reset or transition back into an operational state simply because the underlying condition cleared. It requires explicit action, a manual clearing, or a key cycle to ensure the driver acknowledges the critical nature of the issue before allowing the 400V system to re-energize.
So it prevents autonomous restarts into potentially dangerous conditions.
Exactly.
Let's focus now on the functional deep dive, maintaining concrete quality and efficiency. We start with loading mode. It sounds simple. Spin the drum at a specific RPM. But the physics of handling falling aggregate make the control challenge far more complex than a cruise control system.
Oh, absolutely. Loading involves massive, unpredictable load shocks. When tons of aggregate, sand, and water suddenly drop into the drum, the load on the motor instantly spikes.
And a simple reactive PID controller wouldn't handle that well.
Not at all. The sudden shock would cause a dramatic RPM drop, creating a large speed error. The controller would then reactively surge power to catch up, leading to oscillations, stress on the drivetrain, and poor mixing quality.
So the SCU needs something predictive, something that gets ahead of the error signal.
Exactly. It employs an advanced control strategy, PID plus feed-forward control. The crucial insight here is that the SCU constantly uses the motor control unit's real-time torque estimate. We'll call it testis.
And the MCU is measuring the current required to maintain speed.
Correct. When the load drops in, the test surges instantaneously, often microseconds before the rotational speed, omega, even registers a significant drop.
So the SCU uses the torque demand signal as a predictor.
It acts as an immediate predictive signal. The feed-forward term instantly proactively boosts the current command to the motor, compensating for the anticipated load shock. This proactive compensation is what ensures the system meets the high-precision KPI, keeping the steady-state speed error to less than plus or minus 0.5 RPM.
Without that predictive element, that level of stability would be impossible.
Impossible in such a dynamic load environment.
That tight control is essential for commercial quality. Now, let's switch gears to agitating mode, the energy-saving focus during transit.
The goal here shifts to economy and stability while maintaining concrete quality. The SCU uses the electric motor to maintain a constant, very low-speed agitation RPM, typically between 1 and 3 RPM.
And this is key because it happens entirely independent of the internal combustion engine's RPM fluctuations.
Entirely. Whether the engine is idling, accelerating, or braking, the SCU maintains that perfect minimal rotation, saving fuel and wear on the main engine components.
And this mode introduces that highly valuable diagnostic feature we saw in the documents, slump monitoring. This must be a huge value add for the fleet owner.
It's a major competitive advantage, moving quality control from manual checks to real-time process monitoring. Slump refers to the flowability or consistency of the concrete, how wet or dry it is.
And if the slump drops, the concrete is starting to cure.
The SCU automates this by continuously monitoring the motor torque, the speed, and the mathematically estimated volume in the drum. It maps these variables, often using a lookup table or empirical model, to estimate the concrete flowability.
So if the motor has to work harder than expected to maintain 2 RPM for a given volume, the SCU infers the concrete is thickening.
Precisely. If that estimated slump value drops abnormally, it means the concrete is setting or going hard. The SCU detects this immediately and alerts the driver or the fleet management system. This proactive quality assurance prevents the commercial disaster of a $20,000 batch of concrete being rejected on site because it's no longer workable.
Next is discharging mode, the critical delivery phase. This requires operational precision and stringent remote safety protocols.
Operationally, the SCU must handle the whole spectrum of delivery needs. It must support high-speed unloading, 10 to 14 RPM, to empty the drum quickly, but also microspeed control, maybe 0.5 to 2 RPM for precise pouring and cleaning.
And since operators are often using a wireless remote control while standing outside the truck, the communication link has to be absolutely secure and reliable.
The safety implications of a compromised remote command, like an unintended start or speed increase, are high. So the SCU enforces strict security. The incoming CAN message from the remote receiver must include a rolling code, which prevents replay attacks.
And a CRC or a checksum.
Correct, to confirm message integrity. But most critically, the system uses a rapid timeout. If remote communication is lost for more than 500 milliseconds, half a second, the SCU must immediately cut the torque and stop the motor. The drum must never rotate out of sight or control of the operator.
Finally, let's look at the scenario every mixer operator dreads: the concrete jam. The extreme condition strategy known as anti-stall or rocking logic.
If the concrete jams the drum, often due to aggregate settling, the resulting stalled motor requires an automated recovery sequence to break that static friction.
How does it detect that?
Detection is based on 3 conditions: motor speed dropping below a threshold, and current exceeding a high limit, and those conditions persisting for longer than half a second.
And how does the rocking logic work? Does it just try to push harder?
No, simply pushing harder often just risks burning out the motor or shearing a gear. The SCU executes a high-torque oscillation sequence. For example, it applies a significant reverse torque, say 50% of maximum, for 1 second.
To loosen the aggregate bond.
And this is immediately followed by a high-torque forward burst, say 80% of maximum, for half a second. This rapid forward-reverse sequence leverages mechanical inertia and momentum to break the friction lock.
And it will try that a few times.
Up to 5 times. If the stall persists, it triggers a severe fault, requiring mandatory manual intervention, usually involving emptying the drum.
Let's talk about the SCU's function as the energy orchestrator. This is crucial for achieving that 20% fuel economy target we mentioned earlier.
It is. The SCU must seamlessly decide which power source, the 400-volt battery, or the chassis engine via the generator, will power the drum, always optimizing for those 5 pillars.
This relies on a sophisticated energy management system strategy that moves far beyond simple battery checks.
It's primarily rule-based logic centered around the battery's state of charge, or SOC. The SCU dictates pure EV mode operation, the quiet, zero-emission mode, when the SOC is above 30%.
So 30% is the comfortable buffer.
It is. But conversely, if the SOC dips below 20%, or if the power demand is unexpectedly high, the SCU immediately requests an engine start or boost via the VCU, shifting into hybrid or charge mode.
Why are those specific 30% and 20% thresholds important?
The gap is important for hysteresis and protection. The 30% ensures there is always a healthy reserve and protects the battery from deep cycling, which degrades life. The 20% trigger point acts as the hard limit to force the engine on, protecting the battery from damagingly low states of charge.
But the SCU doesn't just react to the current load. It needs to anticipate future loads, like the sudden start of a massive discharge.
That's the essence of power anticipation. Relying purely on reactive control leads to voltage brownouts and engine lag. The SCU employs predictive algorithms, like a moving average filter, to forecast high load events based on driver inputs and mode requests.
So if the driver requests a transition from agitating at 1 RPM to discharge at 12 RPM,
the SCU proactively requests an engine speed increase via the VCU before the motor current spike hits. This ensures smooth, instantaneous power delivery and maintains system stability.
and given the huge rotational inertia of the heavy drum, there's a significant opportunity for regenerative braking, which is often overlooked in industrial applications.
It's highly significant here. When the operator decelerates the drum from high speed, that massive kinetic energy has to go somewhere. The SCU controls the MCU to capture that rotational inertia, transforming the motor into a generator.
And that recaptured energy goes back into the battery.
It does. It maximizes overall efficiency instead of wasting that energy as heat through mechanical resistance.
Let's circle back to functional safety, specifically the HRR, the Hazard Analysis and Risk Assessment documents. This dictates the system's design complexity. What did the analysis flag as the absolute highest risk items demanding ASIL-CD protection?
The highest risks universally involve uncontrolled motion combined with the massive inertia of the drum. The HRI analysis assigned high ASIL ratings to 2 critical areas. First, preventing high-speed reverse while the vehicle is in motion. We'll call that safety goal SG01.
Why is high-speed reverse so dangerous?
At speed, reversing the drum rotation could potentially throw concrete out of the chute, or worse, cause structural damage to the mixer body due to dynamic loading, leading to a major highway accident. That consequence demanded ASIL-C protection.
And the second was controlling unrestricted torque output, often from a communication failure.
Yes, unrestricted torque output, or SG04, is highly dangerous. If the CAN bus fails or critical command message is corrupted, like a stuck max torque signal, the drum could run away, causing catastrophic failure or severe injury.
So things like a corrupted CAN message or a freeze in the alive counter.
Were flagged with the highest observed risk priority number, RPN 120, demanding ASIL-C redundancy and protection mechanisms in the safety partition.
So those high ASIL ratings feed directly into specific safety goals, which then cascade down to the technical requirements the engineers must meet. Can we trace that chain?
Absolutely. It's the core of capability development. We trace the requirement from the abstract hazard down to the specific line of code. For example, safety goal SG001, prohibit drum reverse at vehicle speed greater than X kilometer.
Okay.
This translates into a functional safety requirement, FSR01. The SCU must monitor vehicle speed and drum direction and arbitrate the torque command if the condition is met.
Which then refines down even further.
To a technical safety requirement, TSR01. Implement a high-integrity plausibility check within the direction safety arbiter module using redundant speed sensor data. This systematic mapping is the final deliverable for proof of safety integrity.
Finally, we should briefly address cybersecurity. Safety today integrates security, driven by standards like ISO 21434. How does the SCU defend itself against threats?
Given that it controls motion and energy, it's a high-value target. Major threats include malicious injection of false unload commands or forging SOC messages, which could trick the EMS into running the battery dangerously low.
What are the primary mitigation strategies?
We rely on multiple layers. First, secure boot, ensuring only verified signed software can run on the SCU. Second, can message authentication for critical PGNs like speed and torque commands.
So using rolling codes and cryptographic checksums.
Exactly. And finally, secure pairing for the wireless remote controllers to prevent replay attacks and unauthorized control.
So developing this highly complex, safety-critical SCU requires a methodical and rigorous verification strategy. This is detailed in the Design Verification Planner Report, or DVPNR.
Yes, and we follow the classical V&V test pyramid approach.
Outline the pyramid for us. We start at the bottom with models, right?
Yeah. We move from model in the loop, MIL, where we verify the conceptual algorithms and simulation, to software in the loop, SIL, where we verify the actual generated C code. But the core validation step for functional safety and integration is the hardware in the loop, or HIL testing phase.
HIL testing is the crucible. This is where engineers confirm that the safety partition, the ASOL modules, actually overrides the functional partition when needed. You're basically forcing it to fail.
Precisely. This is fault injection testing, or FIT. We deliberately simulate dangerous failures to confirm that the fault tolerance mechanisms are fast enough and robust enough to meet the ASOL CD requirements. The safety goals from the ASRR directly translate into these HIL test cases.
Let's detail the required test cases derived directly from those safety goals. Start with the most critical, preventing high-speed reverse, SG01.
Okay, so test case 1 involves injecting a drum direction command equals reverse signal into the functional partition, while simultaneously simulating that the vehicle speed is above the permitted threshold. The expected result is non-negotiable and timed. The SCU's direction safety arbiter must detect the contradiction and command torque equals 0, immediately transitioning the system to the fault mode.
And that verifies the integrity of the ASIL-C direction monitoring module.
It does.
The next crucial test must validate the rapid response to physical safety breaches like the HVIL, which we established has that 10 millisecond cutoff mandate.
Test case 2 simulates the critical HVIL open signal, a break in that daisy chain via the HIL system. The expected result must prove, with data logging accuracy, that the torque cut command and the associated contactor opening sequence is executed in less than 10 milliseconds. This tests the HV safety monitor module under extreme time pressure.
And what about detecting those compromised communications that earned the highest RPN, the scan failure?
Test case 3 is designed to attack the system's communication integrity. We simulate a CAN message failure, perhaps by freezing the message's alive counter or deliberately corrupting the CRC checksum on a critical PGN.
And the expected outcome is a two-step graceful degradation.
Right. First, a torque derate limiting power as a warning, and then a full stop fault state if the communication error persists for a defined safety period. This validates the CAN safety monitor and the fail-safe logic of the torque safety monitor.
This systematic testing and documentation process is about more than just checking boxes. It's about building institutional knowledge and competence. This is where the mandatory requirement for engineering traceability becomes paramount.
The trace matrix is the final proof of competence and compliance for ISO 26262. It provides the systematic, auditable record. It connects every abstract safety concept to a tangible test result.
And the chain must be unbroken.
Unbroken. From HR to safety goal to functional safety concept to technical safety concept to a specific software module like the direction safety arbiter.
All the way down to a specific software runnable and the specific HIL test case.
Exactly. That systematic mapping provides the irrefutable evidence that the engineering team understood the risks, designed the countermeasures, and successfully validated them under simulated failure conditions. It's the direct deliverable for capability development.
And ultimately, the success of the entire SCU development process is judged against final, quantifiable key performance indicators that tie directly back to the 5 core mission pillars.
That's the bottom line.
Let's summarize those KPIs.
Okay.
What quantifiable targets define success for the SCU development team?
On the economy front, the target is clear. Achieving a fuel consumption reduction greater than 20% compared to a traditional engine-driven hydraulic system.
Okay.
On the safety front, the ASIL CD fault detection and mitigation response time must be less than 100 milliseconds for all critical failures, with the exception of the HVIL, which is 10 meters.
And finally, reliability.
Reflecting the core value proposition of reliability and quality assurance, the system availability must be rigorously proven to be greater than 99.5% during operating hours.
What an incredible deep dive into a system that is fundamentally changing how construction machinery operates. We started with what looked like a simple, heavy vehicle, but we've traced the engineering journey of the SCU from a basic controller to the complex, safety-certified core energy and motion coordination center of an electric construction machine.
This functional specification process adopting ACE-style CD rigor, designing the software with strict partitioning using the safety gate principle, and executing the full DVPNR strategy shows the commitment required to deliver on all 5 mission requirements.
Power, economy, safety, comfort, and environmental compliance.
All while managing 400 volts of electricity in the harshest industrial environment imaginable.
And the most profound takeaway is the systematic approach itself, the full traceability chain from hazard analysis to hardware-in-the-loop testing. This isn't just a bespoke solution. It represents a mature, reusable engineering capability.
It is. This SCU architecture was deliberately designed not just for one mixer truck, but to be a highly modular, safety-certified core foundation. The components, the partitioning structure, and the communication protocols are generic enough to be adapted.
Which raises an intriguing, provocative thought for the future of off-highway technology. If this robust ASIL compliant system can meticulously manage the high-stakes, dynamic control of a cement mixer drum, which is arguably one of the hardest processes in construction, what implications does this hold for the rest of the specialized, heavy-duty construction vehicle market?
Is this systematic, safety-driven SCU the true blueprint for software-defined vehicles for off-highway applications, ready to manage the complex, mission-critical operations of the next generation of cranes, excavators, and dump trucks?
The heavy industry is officially going electric, and the software is leading the charge.